Ready? Good evening, members. Welcome to another fantastic webinar by SAE India. This time it is about aerospace, the lesser known sector amongst the programs in SAE India. That is a popular perception. Human mobility has made monumental leaps in the past century. Despite many stops and starts, engineers have been able to make men fly and the earth move. It all started in 1908, and then in 1925, Fokker debuted with the F-7B-3M, the first modern tri-motor aircraft. Then the Boeing came in 1957 with 707, the first American-made airliner to enter commercial aerospace. In the next 21 years, ladies and gentlemen, more than 700 of them would be sold to the world's airlines. 1961, another milestone in SAE's aerospace industry, thousands material specification of SAE in aerospace was published. 1970 came Europe. Airbus Industries formed as a multinational between Germany, England, and France, and then they went on to design and produce A300s and another successful aircraft. The world's aerospace industry has gone through several evolutions and revolutions over the past 100 years, and so do SAE. Society of Automotive Engineers was and is an integral part of the global aerospace industry. In India, SAE India got formed 25 years back, and our aerospace board celebrates its 11th anniversary this year, in fact 18th December. We are 11 years old as far as aerospace is concerned. We've been hosting a parallel technical conference in almost all the India's aero show events, mostly in Bangalore, but this time it will be in Gujarat sometime in February. We have conducted several professional development programs, lecture meetings, roundtables, CXO roundtables, and student competitions in the aerospace. 2 years back, ladies and gentlemen, based on the similar lines of Aerotech, SAE India has conceived AeroCon, Aerospace Conference. And thanks to little virus, it was supposed to be in-person conference, got converted into digital, and we have instituted that as a biennial conference, which means every alternate year we have AeroCon. The next AeroCon is in June, AeroCon 2022. Expect more from us. Coming to the topic in the aerospace industry, ladies and gentlemen, simulation-driven engineering. It has always been a fascinating topic in the last 25 years, especially for me. I am Venkatraj, Deputy Director General, SAE India. I started off as a CAD/CAM person. In fact, CATIA, the world of products, Simulia, Innovia is very close to my heart because I served IBM in India as the PLM product manager for almost 5 years. So the development of innovative products and technologies with modern approaches and instruments is gaining more and more importance today. The CAE technology contributes decisively to shortening and optimizing new product development cycles in many areas, so to say, especially in aerospace engineering. Aerospace and defense in particular, this saves both time and money, which would have been spent on cost incentive test runs without sacrificing the product quality. So it's an interesting topic we have chosen, and thanks to 3DS, Dassault Systems. Our topic for today's lecture is simulation-driven engineering in aerospace and defense industry. I am indeed very happy to introduce Mr. Darshan Dupati, Simulia Industry Process Consultant, Dassault Systems. Mr. Darshan holds a master's degree in aerospace engineering from a famous university based out of Toulouse, which is ISAE Supero, France, and has industry experience of 6 years in the field of aerodynamics and acoustics. He is working as an industry process consultant at Dassault Systems. Darshan works with automotive OEMs, providing solutions related to aerodynamics and acoustics. What is very interesting about Darshan is he has worked with several Formula One designs, and in fact, Darshan SAE India is known for Supra, the acronym for super racing, the answer to formula. We are forbidden to use the word formula because of patents. So there is nothing but the formula answer for Indian students. So I welcome you to join the Supra competition, which happens every year in Buddh International Circuit, which is a $1 billion circuit in India or in Asia. So Mr. Darshan, prior to current role, he has worked as an aerodynamist with several motorsports teams such as Toyota Motorsports, Germany, Oreca Motorsports, France, including Formula One team. Very glad to know that. Manor Racing in the UK. He has special interest in working on flow separation control, drag reduction, and shape optimization. If you belong to racing or Supra team, you know the importance of drag reduction. It costs you a lot either way. So, welcome Darshan for today's seminar. I'm moving on to Ms. Emmeline Vatsalan, Simulia Industry Process Consultant, Dassault System Worldwide Simulia Fluids Industry Process Consultant Specialist. And very interestingly, Emmeline is Emmeline is a graduate from Tamil Nadu with a super score of 9.12 out of 10. That's like a wow. She went on to become the master's out of Cincinnati, worked in EXA, and then now with Simulia, which is a part of 3DS, a group of companies. Welcome, Emmeline and Darshan. Ladies and gentlemen, I hope you will have a technology-filled session today in simulation-driven engineering and A&D. Over to you, Darshan and Emmeline.
Thank you, Venkat. That was a beautiful introduction for both of us. You beautifully set the context for today's webinar. Let me share my screen right now and let's get started with the session. I request you to please confirm if my screen is visible.
Yeah. Okay, go ahead, please. I think your screen is visible, so.
Give me one moment.
Yes, stop video.
Let me share with you the screen again. Right.
Yeah, the screen is visible.
Okay, so I'm getting started with the session. So I welcome once again all the participants to this session on simulation-driven engineering for aerospace and defense industry. So my colleague Darshan and I will be presenting the first, myself the first, and Darshan the second session. And we will have the Q&A session right after my presentation and also after Darshan's presentation. So please feel free to drop in your questions in the chat window so we can try to answer them here. So if time exceeds, we will try to reach you out on your emails or your contacts to answer your questions. So let's get started. So today I have the following outline. So we will quickly walk you down through these following topics. So this will be focused mostly on the simular fluids portfolio, right? So initially, I would like to tell you a brief overview about our company. So we are Dassault Systems, the 3D experience company, and we provide business and people to imagine sustainable innovations. And we are a purpose-driven company, and we believe in progress and innovations in terms of balance and impact. So we are about 20,000 passionate people from over 130 countries, and we have about close to 3 lakhs customers spread worldwide, and we serve 11 different industries in over 140 countries, and we have about 26 million users of Dassault System products. And the game-changing flagship product is the 3D Experience platform, through which we support the customer and inspire people to sustainable innovation. All right, and our vision is, as I said, is to provide business and people to imagine innovations that are capable of harmonizing product, nature, and life, which means we want to live sustainably, and we believe that this is possible only through the engineering technology. And we profoundly believe that the virtual worlds extend and improve the real world. So there is no such thing called rehearsals in the actual world. But in the virtual world, we can simulate, we can evaluate the impacts that a product is having on the ecosystem. So before even the product is being produced, we can leverage and exploit the virtual world in order to have a sustainable future. And we inspire and support our customers in order to leverage the virtual world through simulations and improve and have a sustainable future. So now that we have seen a good overview of Dassault Systems, now I would like to step into the next topic, which is the industry challenges that the aerospace and defense industry is facing in today's world. We all know that this is the age of digital transformation. And in this age, there are a set of challenges that the industry is facing. In specific, the aerospace industry's biggest challenge is the budget and the time constraint. So today, the A&D industry is facing the difficulty in controlling the cost overrun. And also it is missing the delivery deadlines. And this has not been a rare case. This has become a usual or common scenario in the past decade. Excuse me. So this is one biggest challenge with regards to budget and time constraint. The second and the closely related challenge is the growing complexity of the programs. We all know that the modern aircrafts are taking in a number of new technologies, and it is being built with using new materials, and complex and new systems are coming together in order to develop a modern aircraft. So therefore, the program complexity is also increasing. So in order to face the growing complexity of the programs, the aerospace industry needs to leverage new technologies based on simulations. So this is another challenge. And the third challenge is the green aviation, meaning less impact on the environment. Like many other industries, now the A&D industry is also under pressure in order to meet the need for more efficient, cleaner, and more importantly, quieter aviation. So this is another challenge. Last but not the least, just like how Venkat clearly put it as a revolution, as a term revolution, I personally think, and we as Dassault Systems believe that we are already in the third aerospace revolution. The space travel has come to fruition, and we have personal air taxis that are being developed, and we have competing startups that are playing very well in the market, and they are coming up with innovative aircraft architecture and novel methods to develop the airframes. So the A&D industry needs to figure out a way to face this challenge of third aerospace revolution. Now, let me tell you some brief overview about the product development methodology. So this triangle, this representation is coming from a presentation that was jointly done both by Boeing and Airbus. So in this triangle, we have the three extreme ends: flight test, numerical simulation, and wind tunnel being the extremes. And we have all the circles in between. So let me explain to you. The pre-development phase, the preliminary aero design phase, and the aero database. For many years now, these three action items were using wind tunnel testing and also the numerical simulations in order to do all these actions. Whereas when it comes to the validation and the certification part, people in the industry usually go to the flight testing for more accurate results, right? So this was the industrial practice for many years. But now the trend is changing. So today the industrial practice is changing, in which all these action items are slowly moving towards the numerical simulation. Why? Because in the earlier industrial practice, if we had used all those action items, we've been waiting for flight test for years and years, because there's a long lead time in order to perform one physical testing. And when it comes to the flight testing, that's another different story. So in order to have a compressed time to market cycle, people in the industry are now shifting their attention to a digital environment, which also means the certification is also done by analysis. So therefore, we need to convince the certification authority, saying that, see, here I have a high fidelity simulation tool that covers the full flight envelope, and I can do my certification by analysis without any fault. I can faithfully reproduce what the flight test gives me in the results. So this demands for a high fidelity simulation tool. So now with this industrial practice, which is developing, which is emerging in the industries, the time to market cycle is compressed. Now we do not have to think about the physical testing. It can either be reduced or even be replaced by the numerical simulation. And just right after the preliminary or the detailed design phase, we can straight away jump into the flight test or the prototyping test, right? So this is the industrial practice that is emerging. So now, how does Simulia play a major role in this, in addressing this particular concept to certification by simulations? So let me give you an introduction about Simulia. This is the snapshot of the technology vision of Simulia. So to me personally, this is a favorite slide because this completely covers what I need to say about Simulia. So on the x-axis, you are looking at multi-physics, and in the y-axis, you are looking at multi-scale, ranging from micro scale to a functional level. So from a coupon level to a full-scale system level. So you can see how Simulia is addressing different disciplines in the market, starting from structures to bio to thermal and fluids, and it can be solved at any accuracy level, starting from microscopic to functional level. Today, in specific, we will be focusing more on the fluids pillar, and we will look at the offerings that Simulia has to cater to the customers when it comes to the Simulia fluids portfolio. So in Simulia Fluids portfolio, we have two major technologies and three major tools. So the two major technologies are nothing but the RANS based solver and the LBM technology. And the three tools are nothing but the mainstream CFD, which we also call it as 3D experience CFD, which works based on the RANS technology. XFlow and PowerFlow works based on LBM technology. So this mainstream CFD is platform embedded, and it has got the body fitted, the meshing technology is robust, and it has got some good hybrid mesher, hex dominant mesher, body fitted meshing capabilities, which is which is integrated to the platform. Now, the highlight of mainstream CFD is it is CAD embedded. So it is integrated with the CAD. So whatever CAD design changes you make, that will immediately reflect in your CFD settings, and therefore you do not have to revisit your setup for every design change, but rather just make the design changes and run the CFD simulations. It is embedded very well, and it is integrated so very well that right after the design changes, you can have the CFD simulation results, and it is completely model based rather than file based approach. Coming to the Xflow solver, so here we have different flow models available. One is single phase, and the other one is multi-phase, and the other one is free surface flows, and that true rotating geometry capability is very much possible in Xflow. And we have inbuilt FSI solver. We have 6 degree of freedom capability here. So we will look in detail about what all other things that Xflow can possibly do. And coming to the last one, which is the part flow part flow, which is based on the LBM solver. This is the world leading best in class transient solver. So this has the meshless technology, which is proven for high fidelity, and it is suitable for aerothermal, aeroacoustic, and cabin comfort sort of problems, which is more relevant for solving unsteady and complex airflows. So let me give you some of the benefits of the LBM based CFD. So here you are looking at a landing gear which has very fine details, like minute details are also captured, and the flow is highly complex and it is highly unsteady. LBM based CFD, which we call it as Xflow and part flow, which uses the LBM technology, is inherently unsteady. So whatever solution you have is time accurate, right? And let me give you the advantages. So here we are looking at the real world geometry, and this real world geometry can be accurately captured in the simulation. You do not have to do any simplifications in the geometry. So since this is using particle based approach, this can handle any degree of complexity in the geometry. And also unsteady flow, as I said, it can capture very well. So the high transient fluctuations can be captured very well. And it is known for its proven accuracy because this methodology is being developed in partnership with established institutions like NASA, etc. So we have best number of white papers and publications available for its accuracy. And last but not the least, this is highly efficient and it is proven for good scalability performance. So you can run it over any number of thousands of cores, and this will have reasonable efficiency and reasonable accurate results as an output. So today in the session, we will look at some of the fluid solutions that these solvers can address. So I will take you through the first three solutions, from aerodynamic performance to optimization, and my colleague Darshan will begin with the acoustics, aircraft acoustics to FSI. So let us begin with aerodynamic performance. So under aerodynamic performance, some of the subtitles that I would like to cover is listed here. So let us begin with the flight envelope. So let me tell you first, start off with the simulation challenges. So here we are looking at a full flight envelope of a typical transport aircraft. So here there are two major regions. One is the flap up and the other one is the flap down. So the flap up condition, as we all know, it is a clean wing cruise condition with smooth geometries, no problem at all, and you can simulate it with any available code. Any available code in the market. But when it comes to the, give me one moment. All right. So here, when it comes to the region number 1, which is the center of envelope, that is called as a cruise condition. So this can be handled by any traditional code in the market. But when it comes to the second through fourth region, which starts off with takeoff. So basically the flap down condition, which is usually the case in the takeoff and landing and low speed stall. So that region may introduce highly transient flows, which are unsteady in nature, and to capture those unsteady flow, any traditional CFD would struggle at that point. And also when it comes to the region number 3, so here we are looking at the yellow dashed lines. This is called as the buffet boundary, beyond which there is buffeting happening, and we can expect high speed stall regime in that region, and any traditional CFD code would struggle to capture the highly unsteady flows in this region as well. And not only in dry condition, but when you talk about the fourth region, which is the icing condition, so any certification authority would not only have the flight tested for the complete envelope in dry condition, but also for the icing conditions. So in order to have your flight or flight component tested for the full flight envelope, that is actually the biggest challenge for the certification. So from the concept to certification, you are using a simulation tool in order to cover the complete flight envelope and have the highly accurate answers, faithfully reproducing what the flight test would give you, or what the wind tunnel testing would give you. So the first, except for the first one, the last three regions would be a challenging task for any traditional code to solve. So that is where our complementary code, which is LBM based, would come into picture, solving highly transient fluctuations. So let us look at in the next slides. So here, through Simulia CFD solution, we are taking CFD from the center of the flight envelope, which is just the steady state simulation and smooth geometries, to exploring the entire flight envelope, which also has the unsteady simulation, separated flows, and fully detailed geometries. Just as you know, when the flap up or the flap down condition is there, so we have some cavities to be considered, and we have highly complex geometries to be considered in that case. So we can capture those minor details in the geometry as well, and predict the precisely predict the unsteady flows. So let us look at some of the workflows. So starting from the cruise condition, we have the 3D experience platform CFD, which will address this cruise condition, which is RAMS based. So here we are showing you a model which is developed in partnership with Wichita University at the National Institute of Aviation Research. So here this geometry is particularly fully parameterized. And as I said, the CFD on the platform is completely integrated with CAD, and it is whatever CAD design changes you make, the CFD simulations can be run automatically for those design changes, and the mesh gets updated automatically. You do not have to come and update the mesh every time manually. It is all automated. So the mesher is pretty robust. So we have a body fitted hex dominant mesh where the prisms are put in the boundary layer, and the most of the fluid domain is filled with the hex dominant meshes, in order to reduce the overall turnaround time. And the user interface is pretty simple. So we have flow conditions, and the boundary conditions can be directly specified without any complexity. And we also can perform the process automation. Say, for example, you have number of design parameters to be run for different boundary conditions. You can set up a loop, and the process automation can be done on the platform. So let us now look at the validation for this particular configuration. So as you can see, the lift CL versus alpha graph is being plotted here, and we can see that the experimental results are in close agreement with the wind tunnel data. And when we look at CD versus alpha curve, we can see close match for some points, but when the angle of attack increases, there is a slight discrepancy. So now this hits the limitation. So here the linear range of cruise condition is crossed, and therefore the non-linearity can be predicted well by using the complementary technology, which is LBM based. So let us now look at the next workflow, which is the high lift configuration. So here you are looking at a wind tunnel testing, or the test case that is coming from the drag high lift prediction workshop. So this is the test case. And we are looking at some separations in the wing tip and the trailing edge and the main wing. Some flow separations are happening, and towards the inboard, there are some inboard vortices. So now this is pretty complex, and the flow is purely unsteady and we can see some separated flows as well. Let us now see how this is predicted using power flow, the transient CFD, which is based on LBM. So here the towards the wingtip, we can see the separated flow region, which is exactly captured in the part flow streamlines picture. And also we can see that the main wing has got some flow features that are also highly precisely captured. And the best part is the inboard vortices, or the flow separation that's happening in the inboard region. This is highly complex one to be captured for any CFD tool, but with the LBM based technology, this can be precisely captured, right? And here we are also looking at the CP plot, and this is actually a validation. So done between the experiment and the power flow simulation. So we can see that the CP graph is highly matching. It's precisely matching with the experiment, the power flow results. Remember that we are looking at the pressure coefficient um, at an angle of attack which is close to 20 degrees, and we are looking at some CL max. So the prediction of CL max is accurate, and also the pressure distribution for such a higher angle of attack is also precisely captured. So this is favorable for any high Mach number or high load factor or high angle of attack kind of problems. And we also have the delta wing aerodynamics. So here we are again looking at a highly swept wing, which is giving you a high lift configuration. So here we are again seeing the experimental result with the power flow result, and the flow features are actually accurately captured. So the next one is the Buffett onset. So here we will see the flap down condition. So here, as you can see, the flaps are in bent down, and we can see the flow features that are highly complex. So at minimal angle of attack, say 2.83 degrees, this is pretty simple to be captured by any tool. So this is good. But when it goes to a higher angle of attack, there might be shocks introduced. Shocks begin to appear on the surface of the wing, and therefore the shock induced separations may also occur. So here in the experiment, you're actually seeing the wave motion that is happening. So towards your right is towards your left is your experimental result, and here we are looking at the power flow results. So here the wave motion is also captured in the experiment, which is also precisely captured in the through power flow simulations. And not only at 5 degrees, but when you go higher at 6 degrees, the match is even better when it climbs high. So we are in close agreement with the experimental result. Right. And also, this is a post-stall regime. So prediction of post-stall and the Buffett onset is also accurately captured using the power flow simulation. So here you are also looking at CL versus alpha curve. So for any CFD or traditional code, we may be able to look at till the stall angle of attack, the flow till the stall. But beyond the stall region, the lift curve becomes inaccessible for any traditional code. But here we are actually looking at the flow behind the post stall region as well. So the post stall regime is also accurately captured. And moving on to the next workflow is icing. So icing here you're actually seeing the ice that is scanned from NASA Glenn Center. It may look complex. It may not be this complex in real aircrafts, but looking at the geometry itself, you may understand the complexity of the flow features as well. So this highly complex geometry may not be even be able to mesh in some of the codes available in the market. But here, the degree of complexity doesn't matter. The mesh works perfectly fine, and you can see the complexity of the flow behind this icing condition. And we can also see the surface streamlines being matched to the experimental result. Right. So with this aerodynamic performance workflows, with the current process, number of configurations are tested in wind tunnel for new aircraft model, and the CFD is largely limited to only the center of the flight envelope, and the turnaround time may take even a year. The lead times are even longer. But with the future process or with the current process of simulation being introduced upfront in the overall product development cycle, we can replace 50% of the wind tunnel configurations with unsteady CFD. And through all these workflows, by now you should have understood that the CFD can be used for the entire flight envelope from concept to certification, exploring the complete flight envelope, not just limited to the center of the envelope. And this is actually a smart testing by having number of combinations, both wind tunnel and simulation, and we can continuously update the digital model. There is no loss of digital model here. So you prepare one model for aerodynamics and use it for reuse for the acoustics, for the cabin comfort and whatnot. So there is a digital continuity in this particular process. And I would also like to show you some of couple of other slides with regards to the propulsion system aerodynamics. So we all know that the engine design also requires aerodynamic performance to be assessed. So here we are looking at some stationary parts and some some rotating parts. So here, so that is actually captured. So here we have true motion to the geometry, and we can capture the complexity of the flow that is in between, that happens between the stationary and the rotating part. So that is what you're seeing right now. And one more thing that we can do is engine and airframe interaction. So having an engine as a standalone and performing the aerodynamic simulation is different. But when it is installed to an aircraft, the behavior might change. So that is what we can capture using interaction aerodynamics. So here we are looking at how the propulsion system is interacting with the fuselage airflow, and for different angles of attack and different Mach numbers, the flow itself is changing. The flow behavior can be accurately captured. So here I'm showing you an example where Airbus, in partnership with Dassault Simulia, developed a thrust reverser unit in a matter of 80 days. And so here Airbus is using the 3D Experience Center in Wichita. So here we can see the thrust reverser being used, and how the complex airflow and the unsteadiness of it is accurately captured. And therefore, from concept to the prototype, just in 80 days, then think of how much more this can be efficient when it comes to the real aircraft development. So this can drastically reduce the overall turnaround time. And we can also look at the surface pressure distribution over time as well as averaged. And so this may using this, we can validate new solutions digitally and launch them without any delays. And the last subtitle in the aerodynamic performance is the cabin flow analysis. So not only the exterior aerodynamics, but also the internal cabin flow analysis can also be done using the 3D Experience platform. The hatchback unit can be optimized. So based on the flow analysis, we can decide on the vent sizing, and vent optimization can be done. And today, the need of the hour is whether a pathogen is spreading, inside a cabin. So that also can be done using 3D Experience platform, because we have the multi-species capability. So using which the air quality control can be modeled. And based on these analysis, the number of vents can be decided, and the number of seats can be decided. In fact, you can change the number of the seating configuration can be changed just because it is CAD embedded CFD. We can quickly see how many seats can occupy the space and how many vents are required for such a seating configuration. So this is one thing, and here you can see the hatchback and cabin detail geometry used in the simulation. And also we have best in class human comfort model in PowerFlow, which can accurately predict the passenger comfort, the local comfort, as well as the overall comfort. And the next title here is the aircraft maneuvers, under which I'll be talking about stability and control and flight handling. So this is going to be real quick. So here we are looking at X-Flow simulation. So the first animation is showing you a no-sub condition. So basically you are enabling a rigid body dynamic model. So you're putting in a drone in the fluid domain, and it is fixed in 2 degrees of freedom, and it is allowed to move in 1 degree of freedom. And you can see how the flow fluctuations happen and how the damping occurs. And in the second animation, you are looking at a flap actuated for a particular amount of time, say 0.5 seconds. The flap is actuated and then it is left off. And you can see how the damping of the flow fluctuations happen and how the response is accurately captured. And here you're looking at a spin maneuver. So here we can enforce a motion. So rather than having a rigid body dynamics model, we can also enforce a motion and see the flow behavior around the aircraft. And not only that, here we are looking at a pitch maneuver. This one is allowed to have rigid body dynamics motion in 1 degree of freedom, which is pitch rotation. And then we can see how the flow behaves. So the pitch oscillation and damping, how it occurs after the pitch up of 5 degrees left off in the fluid domain. And the response curve is also captured. And moreover, this is a Dutch roll. So this one here is allowed to rotate or move along all the 3 degrees of freedom. So pitch, yaw, and roll rotation are possible, and then figure out how the flow changes, flow behavior impacts the motion of the aircraft. So this is the inherent FSI solver coming into picture. So where the flow forces are interacting with the body and changing the position and the orientation of the product. And not only this, it not only has the inherent FSI solver, but it can also be integrated with a secondary tool, say a structural solver, for example, Abacus, and it can have a co-simulation. So basically the fluid forces can go to the structural solver, and the structural solver in return can give you the new orientation and position of the aircraft. And the last topic for my presentation is the optimization part. So here, as I was telling you that, the highly complex flows can be captured very well. Not only that, we have a latest functionality which is called as design guide. So using this design guide, an engineer can be guided through the design process. For example, here we are showing you a transonic or a supersonic business jet. So here on the right, you are actually looking at the features or the design variables that can be changed in the simulation. And to your right, you are seeing the response curve, basically the aerodynamic performance, the CL/CD graphs, right? So if I move further ahead, so here you are looking at how the wing twist affects the CL/CD performance. So as and when you change the scroller, you can also see the CL/CD performance corresponding to that particular design variable. Not only that, if you switch to the guide mode, so there is a second mode which is called as a guide mode, which will give you more insights such as a Pareto graph using which you can do a design trade-off. And here also you can, this color map will show you how to move your geometry towards the optimal point. So those kind of design changes can be done using this design guide. So this is the design optimization. And not only that, we can also integrate multiple disciplines inside the platform. So here, for example, we are showing you a CFD model built and as well as a structural model built for this particular drone model. So whenever the design change is happening, say for example, the flap angle is changing, so then the mesh, both the structural and the CFD mesh gets automatically updated, and therefore you will be able to do both CFD and the structural analysis together simultaneously on the platform and do a FSI simulation. So here towards the end of the video, you will be able to see the results. So basically you will signify the interaction surface for the fluid structure interaction, and you will be able to look at the results like this towards the end of the simulation. So integration of multiple disciplines is very much possible on the 3D experience platform. So the last subtitle that I wanted to discuss is the multidisciplinary optimization. So far we've been seeing, aerodynamic performance and maneuvers and things like that. Now, when you want to do a multidisciplinary optimization, including, aerodynamics, structures and EMAC, things like that, then we have the powerful capability on the 3D experience platform. So here, usually in an organization we have file based or siloed systems, and a CAD engineer is working in his own desk with the disconnected point solution, and a CFD engineer would be working in a siloed process, and a structural engineer would come with a different result, and all these. So the unified database management is something difficult for an organization today. It's a big challenge for an industry. What we propose with the 3D experience platform is a model based unified platform approach. So starting from the design to the certification across all enterprises, every solution is connected on the 3D experience platform. In fact, we have done a similar project for one of our customers, which is fully automated. So we have the 3D experience platform in the center, and we did a completely fully parametric wing with a plan form, internal structure, and parameters fully parameterized. And we performed an aerodynamic simulation on that, considering the cruise condition and the dive speed. And we performed a structural simulation for that as well, assessing the upbending and downbending limit loads, doing structural and buckling load analysis. And basically we explored the design space. We did a fully integrated or automated design exploration, and then we arrived at an optimal point. So therefore this ended up with a multidisciplinary optimization. And this work is being published in the 4th National Conference on MDO. So this is jointly done with NAL, and the paper is available online. So the key highlights of this paper on the MDO part is through the methodology that was proposed by Dassault Systems. The concept design exploration phase is accelerated and can be accelerated, and this is a fully automated and integrated MDO process. And there is a shift from file based to model based approach. And instead of working in silos, people get to work on a platform based integrated approach, and therefore the optimization becomes much more easier. And in this paper we have also proposed the industry standard best practice for the concept wing design. And there is no digital loss. There is reuse of the model, reuse of the methodology, and therefore this is a sustainable process. So overall, through this presentation, we looked at different solutions. So as a summary, we can drastically reduce the expensive internal testings and make use of the state-of-the-art fluid simulation solutions. And this will also compress the time to market cycle. And this also enhances the simulation-driven design and innovative designs as well. And this is highly accurate, and it is proven for its accuracy. and it is available for the entire flight envelope, starting from the cruise to high speed stall or low speed stall or buffeting conditions. And through this, we can increase the certification confidence by leveraging the high fidelity CFD methodologies. So this is what I wanted to present, and now is the Q&A session. Thank you so much for your attention. If you have any questions, let me know in the chat box so I can answer them. I have 5 minutes to answer them, and the next session would be continued by my colleague Darshan, and we'll start off with the acoustics of aircraft. Right, I'm going to stop sharing my session and look at the chat window for questions. I can see Darshan has already answered many of your questions. And the last question from Vishnu Vardhan, thank you. So you are asking where can I learn Simulia? You can definitely reach to our website, which is 3ds.com or Simulia website. And you can know more about our solutions and reach out to our experts to learn more. So with respect to optimization, the design optimization, the CFD model used was LBM. And when it comes to the multidisciplinary optimization, it is the RANS-based solver. Yes, part flow is particle-based. It doesn't fall under finite volume or finite element. All right. So Lokesh is asked, as an aeronautical engineer from India, what is the scale and scope in aerospace market next 4 to 5 years? So I personally believe that there is a scope for aerospace or aeronautical engineers in specific, though we do not have passenger aircraft manufacturers in India, but we definitely have good set of private players who develop drone models, personal air taxis, and the urban air mobility is around the corner, and therefore and also Boeing and Airbus are pitching in for their multiple subsidiary units in India. So definitely there is a good scope in the aerospace market. All right. If there are not many questions, I will hand over the platform to Darshan. So Darshan, over to you.
Once again, good evening, everyone. Thanks, Emlyn, for presenting the source system solutions for assessing the aircraft performance, and especially highlighting some of the most difficult or challenging areas, such as high lift configurations or close to stall areas, how well the solution can be used to get a meaningful results. And to end with, multidisciplinary optimization is always an added value, I would say. Today, no one is working on one particular physics. Everyone, to be competitive, is looking at all domains in order to optimize their product. So in that regard, this is definitely going to be an helpful solution for someone who is working for improving their product. With that, let me begin my presentation. I hope the screen is visible for everyone.
Yes, Darshan, we can see the screen.
Thanks for the confirmation. I'll be taking from here about solutions that we have for addressing the acoustics of the aircraft and propulsion system, and lastly on the more complex conditions which involve fluid and structure interactions. let's begin with the acoustics of the aircraft. So in this particular part of the topic, I would be addressing what's the challenges that is going to be faced when someone wants to start looking at the aircraft noise, and then introducing you to aircraft noise solution provided by the source system Similia solutions, and especially will show you how fluid simulation can help in terms of identifying the noise, as well as what's the impact that this noise would bring for the observer or the someone who is at the ground. And let's speak about what's the benefit of the solution that's been offered, and then some of the case studies where we have worked either in terms of validation or the cases where we have actually worked on the project and provided with the design solutions that has brought in the reduction in the noise generated by the aircraft itself. So before we jump in and start looking at what's the solutions that we have, let's try to understand what's the importance for looking at the aircraft noise. Today, we know that air traffic has grown quite tremendously compared to 10, 15 years back. And at the same time, the population is growing and city is expanding at a larger rate. And now there is a lot of habitual land that comes across where the flights are going closer to these areas. So this results for the communities to get exposed to uncomfortable decibels subjected to them all the time. So the lawmakers and the regulation units are coming up with much stricter noise requirements in terms of having a low noise producing aircraft, right? And for someone who is working on the aircraft noise or improving the design for having a lower noise, the three main things that would come to him is firstly, where is noise actually coming from, and how this noise is actually getting perceived at the ground level. Is it high or low, sufficient enough as such? And then how can we actually reduce the noise once you have identified it? So in the course of this presentation, I'll show you how simulation can help in providing an answer to these three questions. So let's take a look at the challenges while someone's improving the design in terms of for the noise. Firstly, like I said, there is an increased constraint in terms of what the noise level that aircraft can produce, set by the regulators, keeping in mind of the communities that the noise is getting subjected to. And then secondly, for the accurate noise prediction, it requires a very detailed geometry of all the aircraft components. Now, getting a geometry with the details being one part of the problem, but the more expanded or the outlook of the problem is ability of the solver that we are using to be capable enough to take all those geometric details into consideration and still able to provide you a valid solution. And thirdly, about reducing the noise levels. First, it's already a difficult problem. On top of that, adds to the problem is not to hamper any of the aerodynamic performance associated to that particular design. Since aerodynamic performance becomes a primary criteria or the requirement, which is a performance of the vehicle, and while we speak of the noise, it's basically the quality criteria of the vehicle and meeting the regulation requirements. And lastly, but not the only challenge, that is, while looking at the noise reduction, it needs to be looked at reducing the tonal noise and then the more challenging broadband noise. So let's look at as an aircraft, what's the typical part of the aircraft that actually contributes for the noise. So here I have highlighted some of the areas which include high lift devices, as wing, which is flap open. It creates a lot of vortex structures, so there is a lot of turbulence involved that interacts with the structure itself. The noise, and we have the noise coming from the engine, fan blades, And the most observed while the aircraft is taking off, landing, the contribution coming from the deployed landing gears, as you are seeing over here. And then, of course, the noise that is coming from the coming from the flow going through the engine, which is basically the jet noise. And today, the source system solution provides or capable to address each of these noise problems, at the same time able to assimilate all the noises that is being measured together and able to give the overall noise that would be generated by the aircraft itself. So here I'm putting 4 points before taking you to the solutions. The 4 benefits that the solution would offer for addressing the aircraft noise. One is, of course, the possibility of assessing the noise sources virtually without having a prototype, and before even you have made a prototype. And also, the fidelity of the solver is so high, it takes into account of all the geometric details that is required without compromising on any of the smallest details, because for acoustics, even the small geometries could account for the overall noise estimation. And secondly, it's about ability to once we have made the assessment of the noise source, its ability to reduce the noise by working on the design itself at the early design stage. And thanks to the well integration of the Similia solver with the design tools available in the platform, it makes this whole workflow simple in terms of the number of iterations that you are carrying out, or the simple way where the design is modified and we get the new results. And possibility of looking at certification or meeting the noise target through simulation, and this is attributed to the accuracy of the solution that it could provide. I'll be showing in the following slides how the solution has been able to provide the degree of accuracy required for the noise assessment. With this, it gives enough confidence to able to use a digital solution to look at if the particular design is well within the target or not. And lastly, having gone through the first 3 would naturally lead to improve product quality. So at the end of the thing, you are going to have an aircraft which is quieter, that is fitting well within the limits of the target set by the regulators. Also, it's going to have a better acceptance in terms of the public. And at some of the areas, it is also true that the airports are going to have a lesser fee for the flights to be landed over there if it is going to have a lower noise footprint on the ground. So in the following 3 or 4 slides, I'm going to speak about each of the benefits that I mentioned through an example on which we have worked upon. So what you are seeing here on the right side is a beamforming data, which is basically a technology to identify the source of noise either during the flight or during the ground measurements, which would be done through an array of microphones, and with the measured data, it can be projected onto the plane or the surface to identify what's the hotspot for the noise. So here we got 3 set of data corresponding to 3 different frequencies, and in the top you are seeing the flight test data shown up, and on the bottom we got the simulation. So if you look at the low frequency, the hotspot is coming from the center of the aircraft, which is actually the noise contribution that's coming from the landing gear. And the simulation is able to predict exactly what's been seen in the flight test, where with this particular information, we can actually get to know, okay, the noise is coming from the landing gears. Now, if we move to mid-frequency region, there is other areas of the aircraft that's popping up in terms of the noise contributors, which is the edges of the flap on both the side, and the same has been seen in the flight test too. And moving on to high frequency region, what we see is still the noise contribution is largely present coming from the flaps, whereas the flight test shows something different, and that's attributed because in the simulation we did not account for the engine noise, whereas this contribution at the high frequency is coming from the engine. So a simulation like this actually helps us in terms of identifying what the source of noise is. And once you have identified the region, then you jump into that particular region and start working in terms of improving the design. This is the second benefit, which is designing for reduced noise. Let's say we have identified what is the source of noise. Say it's coming from the landing gear, and here I am portraying one of the example which we have worked along with NASA, where the intention was to reduce the amount of noise that's coming or generated from the landing gear, and the solution that is being looked at is actually using a fairing, as you can see over here, which is in red. And this fairing has a lot of pores, and all of these pores are resolved and simulated. You will be seeing more details in terms of how this fairing actually has performed well in terms of reducing the noise in the following slides. So starting with identifying the noise source, then we know the source and we worked out certain design improvement option. And then what can be done is to look at how this particular design has uh, resulted in terms of the noise footprint that it would create on the ground. So here we are seeing an aircraft and the noise map which is projected on the ground. So it shows the area around which the amount of noise is getting spread and what degree of noise has been generated. So if it is well within the target limits, it's all good. If it is not, we go back and say modify the design, and then again look at the community noise. Like this, we know well before the flight test is going to be carried out for the certification, we know the design product is well within the limit, thereby avoiding the late stage risks, such as identifying that it may not meet the target when you are actually carrying out the flight test. And the last point I spoke earlier, which is an improved product quality. Having designed for the lower noise, what we would be ending up is with the quieter aircraft, as I said, which is going to be well accepted in terms of regulation requirement, as well as in terms of benefits that you would get in the airports. With this, I want to play one video that highlights the overall process that is involved and what's the kind of details that we actually capture while looking at the simulation results, and how this flow details actually helps us in terms of predicting how the acoustic waves are going to be generated from different parts of the aircraft. So what you are seeing is a concept aircraft that's designed within the systems. And what you are seeing over here is a wing with all the details in terms of slats and the flaps, which has been fully deployed, including the landing gears, and the detail that's present in terms of the geometry. Like I said, it's a concept, but you will be able to appreciate when we are when I'm going to show the real world problem that we have looked at in terms of the level of details that is being taken into consideration. So here you can see all the flow details that's coming from the wing, slats, and all the minute turbulences, which is well captured, which in turn means capturing all the pressure fluctuations that's happening in that turbulent field as well as in the fluid domain. So with this information, we actually can able to generate an information like this, which is nothing but the pressure fluctuations at a certain frequency where the acoustic wave is propagating from the leading edge, trailing edge, and then you see the acoustic waves that's generating from the engine and the landing gear, and all these things is the pure small scale turbulences which is coming from the landing gear itself. Now with the information of all the noise contributors, we can actually propagate that to far field noise, which is basically the noise that going to be perceived at the far location from the aircraft, such as ground in this particular example. So on the ground, what's the noise map is going to be seen as. So the flight is approaching near to the landing, and that is the noise map. And here in this example, we have an observer who is standing on the ground, and the flight is approaching him and then departing. And then we see what is the highest level of noise that he would be observing and how it diminishes once it travels away from the observer. Such detailed outputs can be obtained from carrying out an acoustic simulation. Now, very briefly, I want to show to you the workflow that is involved in terms of addressing the aircraft noise. So it's not too different when we compare to any of the typical simulations that we carry out. You always start with the inputs, what's available, and what is the objective that you are looking towards. The reason for simulation, which could be for reducing the noise or to be having within the target limits, like that. And you begin with the geometry preparation. And again, I emphasize over here, we appreciate to have the highest level of details as the realistic product has to be considered in the geometry, because even the smallest details can have an impact on the noise assessment. And later you start with the simulation setup that would involve what's the speed of the flight is, what's the angle of attack, what's the flap angle that's deployed. All this information is built for the simulation setup, and then we run it in the high performing computers, because acoustic simulation is going to be quite intensive given the nature of low scale pressure fluctuations that needs to be captured well. And then you begin with the post-processing and analysis. So this would involve acoustic post-processing as well as a lot of aerodynamic post-processing, such as flow, separation, etc. Because it's having a right aerodynamic flow is important to get the right acoustic output. And then you will be looking and seeing the output against the KPI or the noise target that is there. If it is not meeting the target, then you enter into some kind of loop which involve geometry modification, setup, simulation. And this loop is going to be quite user friendly, as highlighted by Emblene in the beginning part of the session. The whole solution is incorporated quite well in the 3D experience platform that would allow one to easily modify the geometry, and the rest of the work is carried out by the machine in terms of automated meshing and run, and even automated post-processing can be obtained with the templates. And as a last part, when we have the design that has met the target, we can actually document what's the final status of the design is, and go towards prototyping or the testing. So over the years, we have worked quite a lot on the acoustics by collaborating with various people, and have the experience of working on various projects. And all of that we have actually put together, and what we call as a best practice that would involve all our experience that has gone in terms of developing the process. This would involve templates and say pre and post processing tools, And it's not just about the tools. As I said, it includes the complete process that is required for carrying out such simulations. So any designer can actually jump in and start working on their product towards improving the design rather than spending time in terms of understanding or building the methodology from his side. So in the next few slides, I would like to show some of the case studies where we have been able to deliver the kind of results or the accuracy that would require to make a design modifications, and some of the design improvement solutions that has been proposed that has made the product to be well within the target or so. As a first case, let's look at the landing gear. As I said, what you are seeing over here, it's the real landing gear, and then the geometry version that is taken for the simulation. As I said before, we would like to include all kind of details in the simulation so that we know how each part is actually contributing to the noise itself. And again, more detail looking at the landing gear, you see all kind of wirings that has gone is actually captured for the simulation. And on the top left, bottom left, you are seeing the flow structures that is coming from the landing gear, and you can appreciate the level of details that's present in the flow itself. And on the right bottom, it's a representation of how the acoustic waves are getting transmitted from the landing gear itself. It's one way of visualizing the acoustic flow, but nothing but it's a pressure fluctuation that's happening at a particular frequency. So this particular work, it's not about just looking at the baseline, but and improvising the landing gear for reduced noise using a one of the design method, which is toboggan fairing, which is it looks like a toboggan which is used in the icy areas to slide. Such kind of design is proposed where it's covering the central part of the landing gear. And again, a beam forming technique is used where you have a lot of microphones, and this is going to project what's the noise source is going to be on this plane and this particular plane. So here we have the results from the simulation. So what you see on the top row is the baseline, which is the landing gear as it is, and the bottom is the proposed solution with the toboggan covering, and the first column represents experiment and the simulation. And we see quite well the simulation is able to show us what is happening in the real world scenario as well, in terms of the area where the noise is getting generated from, particularly this area and this particular area. And the same is shown quite good for the proposed solution as well. We see that the noise coming quite majorly from the third wheel and then at this particular junction. But what's more interesting is looking at the plane that is at the bottom section, which is going to be quite an interest for us, given that the noise from the aircraft is getting transmitted from top to bottom, and this is going to give us quite good information in terms of what is the noise that is actually getting propagated downwards. And if you do look at it again, in terms of identifying the areas that is contributing to the noise, the simulation has done a good job in terms of saying the noise would be coming from these two particular areas. And what's more interesting is to see how this particular proposed design solution has actually helped us in reducing the noise that was originally getting generated from the landing gear. So here we don't see a lot of noise that's coming up. There is certain level of noise at this particular corners. Of course, it's true that the noise is not present for this particular frequency of 4000 hertz, where this design is doing a very good job. It could be present for certain other frequencies. It cannot be fully eliminated for all the frequency range. but for this particular frequency, this particular design does a very good job. Now let's look at another case study, which is basically the noise that's coming from the flap side edges. And here it's not about just identifying the noise areas. We have gone ahead in terms of reducing the noise itself. Again, the work is done along with NASA, where they propose two solutions, as can be seen in this green box, which is a small brush kind of structures, and then another one being one which having the pores. And what we see is this particular structures is going to reduce the vortex formation, which in turn reduces little bit the impact of the pressure on the surface of the flaps itself. And here you can see clearly the blue and red regions, which basically depicts the positive and the negative pressure fluctuations that's happening on the flaps. And that gets quite reduced when we look at the flap design with this treatment. This would be coming from the one with the pores. And this particular plane actually confirms for clearly that the level of noise that was coming from this particular design has been largely reduced when we look at this kind of side edge treatment that has been done. Now, I would like to show how similar solution can be used even for addressing the jet noise, what you are seeing over here. It's a simple circular jet, and you see the pressure fluctuations that's coming from it, which is basically the acoustic waves that's transmitting. And on the right side, we see it's directivity of the noise over the 180-degree angle. And what's colored is the level of noise that's coming from the jets, and for a different frequency ranges over a different angle, which is like this, covering from this side to the 90-degree and then going to the rear. And what it shows is simulation is able to produce same kind of results as the experiment, which means you can develop enough confidence on the solutions that's provided by the simulation, thereby going ahead for improving the design for having the lower noise. And it's not just about addressing the jet noise in the isolation. Jet noise can be integrated along with, say, the fans, and then you have the high lift device. So all the installations are kept in place, and we can actually get what the kind of noise that this installation is going to generate. Typically, it's not very normal to optimize a nacelle or engine in this configuration, because it's always been looked as a separate entity and it's been optimized. But when you actually integrate it with the whole installation, the story may be different. And DS solution actually allows even to take into consideration of such complexity and able to get what the kind of noise the overall system may be generating. And last, another case study, very interesting one that I would like to present, is considering the whole aircraft, how it's been used to assess where the noise is coming from, and then also proposing the solution to reduce the noise. So I have put 3 points that that I had highlighted in the beginning in terms of benefits, which is virtually assessing the source of noise, and then once you know the source of noise, designing for reducing the noise, and then meet the noise targets. So we have here two configurations. The left one being a typical wing, where you have the flap in the very um, normal way, where there is a gap. And I would like to pause at certain region over here, and then you have another config where the flap is blended quite well with the main wing, and we see clearly some difference in terms of flow structures and the level of disturbance that present particularly in this particular area is quite largely reduced, which actually helps in terms of lowering the noise levels as well. And that's one of the improvement that's coming from the flap. And then again, looking at the beam forming data from the flight test, what you see is the hotspot coming from this particular region, and we got two simulations for it for ascertaining the location of the noise. So this is actually coming from the landing gear, and while we look at the simulation along with the nacelle, we were still able to identify the source of noise at the center. And when the simulation is performed without the nacelle, we still see that the hotspot present in that particular location. That confirms the noise is largely getting contributed from the landing gear in this particular config. So having known the area to work upon, what's been done is proposing a design solution on the landing gear like this, which is basically a fairing. Two types of designs were performed on this particular concept, which is a solid fairing where everything is closed, and then you see another iteration where you have the black regions, which is nothing but a lot of pores that is involved. So what do we get when we actually simulated this particular design? So you got on the top the spectrum of the far field noise measured for the two configurations, which is the typical landing gear and then the landing gear with this fairing. The black is represent the flight test, and the red is coming from the simulation for the solid fairing, the one without the pores, for which actually the test was actually carried out. And we see a good correlation in terms of the noise levels estimated from the simulation for mid and high frequency ranges, and some differences coming from the low frequency. It could be attributed to certain cavity noise which may not be captured in terms of geometry. However, in terms of overall, there is a good confidence in terms of what's the noise predicted from the simulation to the experiment. And looking at the difference between the two, what's the noise reduction has been, which is in the bottom curve, and we see about 3 to 4 decibels of noise being reduced for almost most of the frequency range. And I want to highlight or emphasize another point here, that all this work was done in the simulation first. We had no information in terms of the flight test, etc. And all this data was present before in hand in terms of the simulation results, and when the test is performed, it reconfirmed what is predicted from the simulation itself. Now, while speaking of acoustics for aircrafts, one cannot forget these days speaking of the air taxi, or say the small jets or the small flights like what we are seeing here, because now it's moving towards a new revolution where it's expected that there is going to be a lot of such vehicles running around the city, transferring people from one place to another. And now that these aircrafts are going to be flying within the city, it becomes quite important that this has to be much quieter, because you are in the city environment where a lot of people are exposed to the decibels that's generated from the aircraft itself. And I would like to show how our similar solution can help very easily able to assess what's the noise it is going to generate, and how well a small tweaks can be made so that you have drastic change in terms of improving the quality of the product itself. So here we have the acoustic simulation performed on the air taxi, and we see that the acoustic waves, which is coming from this particular location as an epicenter. And what's been done is a very simple modification of taking this particular rotor to an higher level compared to what was there. And what do we see as an effect is the level of noise is drastically reduced from the original design. And one of the factor that contributes is the downstream propeller, again breaking the vortex that is generated from the upstream propeller is actually reduced in this particular configuration, thus helping in terms of reducing the structure vortex interaction, a kind of dipole noise that gets reduced, thereby reducing the overall noise of the aircraft itself. And even when we look at what's the noise footprint of this vehicle is going to be on the ground, we see that the overall noise footprint is largely reduced when it is compared with the baseline. Now, moving on from the acoustic solutions, I would like to highlight some of the solutions that can be used for the propulsion system. It could be the turbo blade engines like what you are seeing here, or the rotors of the helicopter, etc. And what I am showing here is one such simulation which is performed on the helicopter blades. And we all know it's helicopter blades are going to be quite complex in terms of its functioning. The blade has freedom to pitch on its axis and then flap on its axis, as well as rotates on a common axis, and there is a lot of movement that is involved. And the thanks to the solver capability that we have, such kind of complex motion can be easily incorporated in the software by giving a simple motion equations like what you are seeing here, just by coming up with an equation that defines the motion. The tool can able to recreate such motion of the geometry. And thanks to the adaptive mesh capability, all these complex maneuvers, even though it is performed, the mesh can adapt to the body very quickly and able to provide right results without having to spend a lot of time in terms of say whether you are getting a right mesh or not. So one such simulation result is what I would like to show here, where the blades were rotating. As you saw in the previous animation, the blades are pitching on its axis, flapping on its axis, and it's rotating. And you see a high level of turbulence in this particular area, because by the time the flaps comes over here or the blades comes over here, it's having a high angle of attack, and then again it goes to a lower angle of attack. And thus with this we can know what's the kind of flow features is, and we can also estimate what's the thrust this particular blades can generate. And since it's asymmetric in nature, what's it's performing, so what is the roll movement or yaw movement it can bring, all this information can be obtained. And another area where it can be used is turbofans, what you are seeing over here, where two different configurations has been simulated for two different RPMs. And the idea is to see what's the kind of thrust that this particular engine can generate for the following RPMs. And if you look at the experimental result and what is being obtained from the simulation, it's not far from what is being expected. So with this, a lot of optimization can be carried out before making your first prototype, and then finally get what's going to be the overall actual thrust that particular engine may produce. And same thing on the different engine setup, where the idea is to see what's the amount of mass flow that the particular engine is able to generate. And again, it's simulated for different RPMs, and we see that one which is in the blue circles that represents the solution coming from the source systems, and it follows quite well with the experimental results with certain level of deviation at the lower RPMs, but quite well predicted in terms of the high RPMs. Now, this brings me to the final section of the my part of the presentation, which is fluid structure interaction, where we can actually look at a complex maneuvers or the complex phenomena that's happening, where it would involve flow interacting with the structure, and structure in turn make some modifications for the flow. Let's look at the first case I would like to show over here, which is parachute, something which is used for decelerating the aircraft when it lands. And what you see here is a structural solver coupled with the fluid solver, and structural solver is able to provide us the information in terms of what's the kind of stresses this particular parachute material is going to experience, whether this stresses withstands that particular material or the cloth is going to torn apart. Such information can be obtained from the structural side, and on the CFD side, what we would get is if that particular flow is able to open up the parachute quite well, and what's the amount of drag that is able to generate, so that in turn you will be able to estimate what would be the landing distance of the aircraft is going to be. And the last two topics, which is ejection of the seat, which is quite difficult if someone wants to try it in reality. As you are seeing over here, you would require a lot of test setup, and then the dummy mannequins to be placed in and assess what's the kind of forces that one would experience. Whereas in the simulation, what we have considered is a human kinematic model coupled with CFD simulation. And with this, we can actually estimate what kind of forces that the pilot is going to experience, whether any part of the aircraft is going to strike him, or if the ejection is not going to be right where the path of the ejection is going to go in the wrong direction. All such information can be obtained with CFD coupled with human kinematic model. And we could also be looking at the stored separation, as you are seeing over here. It's again a fluid structure interaction, but the capability of the solver that we got is doesn't require you to again couple with a certain other tool, where we have an inbuilt rigid body dynamics in the CFD solver. So having the information of the center of gravity of the either a booster or the missile unit, and its weight, and what's the inertial moments of that particular object is going to be, one can simulate such type of simulation within the CFD environment, where the CFD solver can actually identify what the kind of forces that it experiencing due to the airflow, and due to the rigid body dynamics built within the solver, it can actually show the behavior of what's the how the part is going to get detached, whether it's going to strike the main aircraft itself, or it's going to be far away. What will be the location of the booster that it is going to fall? Such information can be obtained with this simulation. So this brings me to the last part of the slide, which is the topic of discussion today, which is simulation-driven engineering. And I want to conclude with this slide saying the solution offered by the source system can actually cater quite many problems that aerospace and defense industry would come across and are trying to improving the product. One being aerodynamics, which we saw, which is for aerodynamic efficiency, and then it can also be used for the propulsion systems to know what's the kind of thrust it is going to generate. And we looked at the maneuvers, which is a more complex aerodynamic situation to address, which would include the dynamic aero loads, and we can also assess what's the stability of the flight, or the damping of the flight is how long it takes for a flight to come to stable condition when it is disturbed. Such information can be obtained. And we saw quite in detail a vast covering on acoustics that would include ability to design on the rotors or high lift designs, or modifying part of the landing gear in terms of reducing the noise, and thereby to also see what's the noise footprint is going to be on the ground, and see if we are going to be within the noise target limits. And we looked at the propulsion basically to identify the thrust loads estimation. It can also be done for blade designs, etc. And lastly, the fluid structure interaction, which is more complex than the individual physics, where you are dealing with 2 or 3 different kind of physics over here. And we looked at store separation, or it could be the ejection of the pilot. And the application is not limited. Wherever we are going to have certain flow interacting with the structures or any other component that in turn also has an impact on the flow itself, can be addressed through FSI simulation. So over in all, I want to conclude by saying the solution offered by the SO system can address the overall domain requirement for improving the product for A&D sector, as well as we can also look at other sectors as well that comes across need for aerodynamics or acoustics and other physics. So with this, I end my presentation and open the floor for the questions. I see some of the questions could be coming. I'm looking at the chat window, although it's a lot. I see that Emlyn has answered quite a few questions already. I'm going to see if there is anything that's missing and provide answer for the same. Okay, I see one question from Vishnu, which is a career based question. Tip for me to work in Airbus, completing the masters. So it largely, as you know, it's quite competitive world right now, and the best way for any of the just graduating student would be the best way to start is with an internship or apprenticeship, where you are exposed to the industrial problem that they are trying to solve, which will be the quickest way for the industry to grab you within the company. That's the best way to begin with. What are the key simulation trends for UAV and drones? Okay, there is a lot of developments that's happening in the UAV sector. It's yet to start over here, although it's in the for the small UAVs. But I'm speaking of scenarios where things have been developed quite a lot in terms for the air taxis that I spoke about. Such developments has happening quite a lot. Mostly in the Europe and in US, where the private companies have come up in building their own quadcopters, or it could be hexacopters, etc. And they are working a lot on acoustics and aerodynamics. Um, and for the small UAVs, again, a lot of activities do happen in terms of the propulsion system, which is basically the blades design. And especially for the UAVs, a lot of activity happens in terms of making the UAV smarter, which means what's its ability to in terms of land mapping, or say detecting the um, destruction events like that. But as such, for the physical development of the UAV itself, a lot goes in terms of designing the propulsion system and the structures. Okay, I see one interesting question from Mridul. How Similia can be compared with other key players such as Ansys Fluent, and where does Similia stands up? So a very interesting question, I would say. One of the key highlights that if I have to put in, that will give you benefit in terms of other solvers would be ability, like I said, ability to take into account of all the geometric details. And it's not just about taking the geometric details. So the way our solver works is that you don't require a separate the mesh. A lot of time you would spend on creating the mesh of the geometry. All that would be required is you have the geometry, and then you just tessellate as it is and then bring into the simulation. And one of the reason why it helps us in that regard is the mesh is automated and works on top to bottom approach, which means you have the geometry that is brought in and the grid that gets projected onto the body, and a new surface mesh gets created on its own. So so in terms of what you have to capture, you don't have to spend a lot of pre-processing effort. um, so worrying about what would be in terms of volume mesh, or it's going to fail, because when you are working from bottom to top approach, you will make sure that the surface mesh is right, and also you make sure certain cavities or the closely placed objects are removed, because it may fail in creating the volume mesh or so, which is definitely avoided. And secondly, the actual dominant point is the accuracy of the solution that's obtained. So especially for the acoustics, and same for the other domains as well. um, we work on the LBM technology, which is basically based on the kinetic theory of gas, um, which actually works on what's the motion of the gas molecules is, particles which is present in the air. Whereas when it comes to Navier-Stokes equation, actually it can be derived from the kinetic theory of gas, and that also comes along with certain approximation in terms of bringing the transport equations and stuff, and the dissipation rate is going to be quite high. Whereas in the LBM, the dissipation rate is quite low and works directly one step above, considering the fluid as a group of particles and how this particle is going to interact with each other. And of course, have to highlight on the acoustics part. We don't actually use a separate acoustic solver like other commercial tools. We purely solve for the flow field and capture what's the fluctuations in pressure that's happening in the flow field, and from that field itself, we are able to get back what the kind of acoustic noise that it would generate. Okay, I see one question on which company uses Similia currently. So cannot pinpoint on a few of them, but I would like to say that the spread is quite wide in terms of all the industry domains. It's been used vastly in the T&M sector, which is transportation and mobility, in the automotive side, and we have its presence in the A&D sector as well, quite a lot. And you saw a few of the examples in the presentation itself, where it's been worked in collaboration with NASA. And we have the other aircraft manufacturers and some of the air taxi manufacturers also using similar solution. And if we look at Similia as a whole, including the structural solver, the its usage spread is quite vast. Okay, I see another interesting question from Jitin. Adaptive mesh and unstructured mesh implemented for LBM. Here, all the mesh that we work on the LPM, it's like structured, which is going to be a lattice, or we can also call it as a cuboidal mesh. And in terms of adaptive mesh, yes, it's well implemented with one of the solver Xflow that Emlyn spoke about, and all the scenarios where you looked at flight making certain maneuvers and then the rotor blades movement, etc. All that place adaptive mesh is coming into picture. Okay.
So Jitin, regarding your question on how is the curved surface treated using structured mesh, let me try to answer your question. So here in LBM technology, we use a robust mesher which is automatic. So in fact, we call it as meshless LBM because it is all automatically generated. So the surfaces, any degree of complexity, it doesn't matter to the to the mesher, because here we use something called voxels and surface. Every complicated, be it a complex surface or a smooth surface, that is going to be having surface generated because of the grid or the volume grid that is outside the object. So wherever the voxels meet the surface, we have the surface generated, and those surface we have the user has basically the freedom to limit the cell size. So based on your curvatures, the arc of the radius, then you can give the corresponding size to fit in the mesh elements. So that's very much possible. Hope that helps.
I was looking at some of the questions from the top. I would take this one last question, which is from Kimberly. What's the average time Similia takes to produce results for complex simulations compared to competitors? Good question indeed. So here, like I said, the two of the solvers that works on the LBM, it's inherently transient in nature, and this solvers since the beginning has been developed, and improvements were brought in, keeping in mind the transient simulations that it would carry out. So the way it has been optimized is that if you are comparing any of the transient to transient simulations from other commercial tools, our LBM solution comes quite ahead in terms of the time it takes for the simulation. Like I said, it has to be always apple to apple comparison. So I'm speaking of transient simulation with the transient simulation. And I have also come across some of the problems where both have been tried on two different solvers, where our LBM tool was able to do at 70% quicker than the other solvers. This is as a real known examples that I have come across. Of course, it all depends on the type of complexity and type of problem that you are trying to solve. But given everything kept same in both the tools, LBM performs quite well in terms of quickness. So I think we are well within the time. If there is no more questions, we can end the session.
Sir, if there is any questions, can put in the chat box, or else we can another session. Yeah, we will send the feedback form to all participants. Please kindly fill the forms, and any questions we can take offline also.
All right. Thank you for your attention.
Yeah,
Thank you, everyone.
yeah, thank you,
Thank
ma'am. Thank you, sir. Thank you.
Have a great evening. Bye.
Yeah, bye. Good night.